Hi to everybody. In this lecture video, we are going to be dealing with chapter 6, and chapter 6 is about some method in the calculus of variation, and the goals of this chapter is to understand the general principle of the techniques of the calculus of variation and to know how to determine the path that gives extremum solution. By extremum, we mean the maxima or minima solution, and to derive the Euler's equation and its second form, and also to understand the several auxiliary conditions which are imposed or which are required, and also to know the delta notation. And of course, you will also be expected to solve the problems on the above concepts. Now, the problem statement of the calculus of variation is to determine the function y of x such that this integral here is extremum. Now, this quantity here is what we call the generalization of the function, or mathematicians are calling it a functional. By functional, I mean functions of functions. Right, now where this y prime is nothing else but is the first derivative of y with respect to x, and the semicolon there is actually used to separate the independent variable to dependent variables. Now, if a function y gives the integral j a minimum value, if this function gives this functional a minimum value, then the neighboring function, no matter how close to y, must make j increase. It must definitely make a increase. The definition of a neighboring function may be made as follows. Right, now the neighboring function must be made as follows, which will be y as a function of alpha and x is equals to y at x plus alpha eta of x. Right, so this is the minimum function of y, and then the neighboring function is increasing this function by a certain variation called eta x, where this alpha can be taken as a scaling factor. Now I want you to picture this as follows. For an example, suppose that you have that function like that. Right, now in this case I will call this one here y of x, and this function here I will call it y of x plus scaling factor times the eta of x, Right, now what I want you to see is the fact that the eta of x, this eta of x is nothing else but is can be pictured as a variation in y. This is just a variation in y. This is a variation in y. This is a variation in y, whereby this alpha is nothing else but the scaling factor, because this scaling here is not the same as here, and is also not the same as the scaling factor there. So the new function will just be defined in terms of this function. So the alpha eta of x is just defined by the variation multiplied by that scaling factor of that a new function compared to the old function. So that's what I want you to see. However, what is also very important is the fact that the eta of x1 at the endpoints, the eta of x1 must just be equals to the eta of x2. That means that when alpha is equals to 0, this function, when alpha is equals to 0, this function here will just be equals to, when alpha is equals to 0, that function of x must just be equals to the function of x. It must just be the same as the original function. So I hope you are able to see that. Now that's what I want you to see. But now what will be the functional of alpha? The functional of alpha for the new function, of course, it will just be catering the y of alpha and x, because that's the new function there. It's no longer a function of x alone, but it's a function of alpha and x. So that will be the new functional of or the new generalization of this function. All right, now in order for us to get the extremum, the necessary conditions, that is the partial differential of J with respect to alpha, at alpha is equal to 0 must just give us 0. It must just give us 0. Right, I hope you are able to understand it. Right, now to make things make sense, let us just do the following example 6.1. Consider the function given by this equation here where y is equal to x, which is just a straight line. Add to y the function either of x is equal to sine x, and find the j alpha between the limits of x is equal to 0 and x is equal to 2 pi. Show that the stationary value of j of alpha occurs for alpha is equal to 0. Right, now from what we have done now from the previous slide, we are just going to solve that equation. Now we may construct neighboring function parts by adding the y of x to the eta of x. Now if we add that to eta of x, this is just going to be the eta of x and multiply by that scaling factor. You remember that scaling factor which makes the new function to actually fit well. Right, now the paths are illustrated in the figure. The paths are illustrated in figure where this is nothing else but y is equal to x, which is a straight line, but this one is just the new function. This is the new function where the scaling factor, of course, here is totally different from there. The scaling factor will be totally different from this graph and to this other one. Clearly, the function eta of x is equal to sine x obeys the endpoint condition. It obeys the endpoint condition because the n at x is equal to 0 and the n at x is equal to 2 pi is just 0 because they are these are just the endpoints. All right. Now to determine the f, so that we can plug it into the equation of the functional j from the previous slide. Therefore, we need to first do the differentiation. When we differentiate this function, this is what you are going to have. When you differentiate that function, this is what you are going to have. And you square this function because you are given f as a square. You square the function. If you square the function, this is what you are going to have. Right. Now, putting things back to the integration, because x1 is equal to 0 and x2 is equal to 2 pi in this case. Now you integrate this function. When you integrate this function, this is what you are going to have. Right, maybe I can just show you or help you to integrate functions like that. Now for an example, I will just take it from, I will start to integrate the integral of 0 to 2 pi 1 dx. This is just going to be equals to, that is just going to be x 0 to 2 pi, and the second term here, and the second term here, the second term here is just going to be plus, it is just going to be plus 2 alpha. The integral, of course, is just sine of x 0 to 2 pi, which is nothing else but it's just going to vanish to 0. This term will just be 0, and then that will be plus the integral of 0 to 2 pi of alpha squared times the cos squared x dx. Now, as I've said earlier on, this term would just be 0. Why that will be 0? Because the sine of 0 and the sine of 2 pi is just 0. The sine of 2 pi is 0 and the sine of 0 is 0. But the first part there, the first term there will just be equal to 2 pi. Right, now we have to do the integration of this term. Now to do the integration of the cos squared x, I want us to use the following identities that I think you still remember, which is the cos of 2x. The cos of 2x is nothing else but it's just equals to the cos squared x. The cos squared x minus, it must be minus, not plus. It must be of x, it must be minus the sine squared x. And also the sine squared x is plus cos squared x is equals to 1. Right, now I want you to make the sign a subject of the formula in this equation here. Now if you do that, you are just going to have the sine of x, the sine squared x is equals to 1 minus the cos squared x. And I want you to take this, you substitute it there. Now if you do that, what are you going to have? You're just going to have the cos squared, the cos 2x is equals to cos squared x minus 1 minus cos squared x. That's what you are going to have. And this is nothing else but this is just equals to 2, it is equals to 2 cos squared x minus 1. That is your cos of 2x. Now if you want to make this a subject of the formula, what are you going to have? You are just going to have the cos squared x is equals to 1 over 2 plus the cos 2x. So that's what you are going to integrate. Now I am sure you still remember that the integral of this, the integral of that is just going to be what? That is just going to be plus 1 over 2x, and now you have 0 to 2 pi, and then plus the sine, the integral of cos 2x is that over 2x over 2, sorry, over 2, that must be multiplied by 1 over 2 and then 0 to 2 pi, and 0 to 2 pi. But believe it or not, this term will also vanish to 0 because of 0 to 2 pi, because of this will just vanish. And then from there, what are you going to be left with? And of course, in here, you should not forget to put that alpha. You should not forget to put that alpha, this alpha squared here, that alpha squared. Therefore, this is just nothing else but it's just going to be 2 pi plus alpha squared pi, which is nothing else but it's just pi plus alpha squared, which is nothing else but that equation that you are seeing there. So that's how you do the integration of this kind of problems. Right, now in that case, those we see that the value of j is always greater than 0. The value of j is always greater than 0, regardless whether alpha is positive or negative. And of course, if alpha is equal to 0, if we differentiate this is just going to be 0, because this will, the j at 0 will just be 2 pi, because we'll be differentiating the constant, because this term will vanish. So this condition is also satisfied. Right. Sorry. Good. Now let us also dive into the Euler's equations. Now to determine the necessary condition expressed, these conditions that, or constraint that we have put, we perform the indicated differentiation of a differentiation in j, because we know what is j. J is defined by the very first integration, which is the functional. Now if we do the derivative with respect to alpha, this is what we are going to have. Now because these points are fixed, therefore this can go inside the integration, and the differentiation only for the integrand, and that is Leibniz rule. And now if you do that, this is what you are going to have for that, because this can just come inside, because these points are fixed and this doesn't affect those points. So this is what you are going to have. Right, now from the definition of the variation of a variation equation, which is this one, you can be able to determine what is the differentiation of y with respect to alpha, which is nothing else but this, but the differentiation of the dy prime with respect to alpha, this is this, and you take this You take this, you plug it to this equation, and when you do that, this is what you are going to have. This is what you are going to have. This is the equation that you are going to have, right? Because dy over d alpha, for an example, is this, and then this other one here is nothing else but is equals to this. That's what you are going to have, right? Now the second term can be integrated using the integration by parts, and the equation for the integration by parts is given by this. I really like this one instead of uv dv and stuff like that, so I prefer this one. So but you can also do it the way you understand it, but this is what you are going to do. Now if you do that, the second part, you do the integration by parts, this is what you are going to have. But I want you to see that this term will vanish, because at the endpoints, the ether of x1 is equals to the ether of x2, and they are just equals to 0, because there's no variation. There's no variation there. So the only term that we are going to be left with is this one here. Now if you take things and you plug it back, this is what you are going to have for the derivative of the functional with respect to alpha. Now for us to have these conditions that we have impose, the whole thing here, the whole thing inside the brackets there, the whole thing inside the brackets there must just be equal to 0. But we also note that we can factor, by the way, we can factor the ether of x. We can factor the ether of x. We can just factor the ether of x, because the ether of x is actually the variation, which is actually totally independent of this other function. Therefore, for us to have this to be equal to 0, therefore this should be equals to 0, and that is what we call the Euler's equations, right? So this cannot be equal to 0 because this is an arbitrary function, as I've said, right? This is what is necessary to a condition for J to have an extremum value, right? Now let us try to do this example 6.2, which is a Brachy-Stochrow example, which is one of the history of the classical mechanics problem, and we can use the calculus of variation to solve the classical problem in the history of physics, which is called the Brachy-Stochrow problem. Consider a particle moving in a constant force field starting at rest from point 1 to a certain point 2. Find the path that allows the particle to accomplish the transit in the least possible time. We want the path, not the time. The time will just be asked on your tutorial test. Now here we just need the shortest path. Right, in this case, I just want you to take your y-axis to be in this, and then the x-axis to be in this direction, and the force field to be actually pointing at the x-axis. Now, if we take, or if we ignore the friction, the friction. Therefore, this field is consecutive. Now, if the field is consecutive, therefore, the total energy of the particle, the kinetic plus the potential energy, is just equals to 0. Now, if that is the case, therefore, if we measure the potential at x is equal to 0, therefore, u at x0 is equal to 0, and therefore, this equation here, T plus U, the kinetic energy plus the potential energy, must just give us 0, because the particle starts at rest. When it starts at rest, the kinetic energy will just be 0. Therefore, this must just be equals to 0. And I also want you to take this as follows. For an example, take this as follows. Say you have a particle placed somewhere here at the corner of this. Now, this is point A. This is at point A. This is at point A, and we want this particle to be somewhere here. This particle will just be moving to that point A, and this is I am putting my x-axis, and then I am putting my y-axis in this case. All right. Yes, that's what I want you to say. Yes, so that's what I am actually putting. Now the kinetic energy is given by this equation and the potential energy is given by this equation. Therefore the velocity must just be given by that. Why? Because you remember in this equation here, of the total the total energy of the particle. Therefore we are just going to substitute that with t plus u is equals to 0. But now we know what is t is 1 over 2 mv squared plus u is minus mgx, which is equals to 0. Therefore rearranging this, we'll just cancel m, and then we end up with v squared is equals to 2gx. And now if we want v is just going to be the square root of 2gx, as you are seeing it there. So that is just going to be your velocity. Now the time required from the origin point, from this point to that point, is just given by this. Why that is the case? That is the case because you remember the displacement the displacement s is equals to vt. But now if I am talking about the small displacement, that must just be v dt. Now the displacement ds, how can you get the ds if I have my x-axis here and then I have my y-axis here? Now the ds is that the displacement is that s. But now if I'm talking about ds, I will just be talking about the dx, and then here that would be dy. Now you use the theorem of Pythagoras in order for you to be able to get the ds. The ds from the theorem of Pythagoras, the ds squared will just be the dx squared plus the dy squared, because I will just be chopping a small here. So this is what you are just going to have. Now you can divide by dx. Now if you divide by dx squared here, and you also divide by dx squared here, what are you going to have? You are just going to have ds squared is nothing else but it's just 1 plus dy dx squared, that must be multiplied by dx squared, because I am just taking this to the other side. Now if you take the square root, there, what are you going to have? You're just going to have ds is nothing else but it's just given by the square root of 1 plus dy dx squared, all under square root, and then dx is just outside the square root. So that is going to be your ds. Now I want us to define dy prime as dy over dx. So therefore, if you have dy dx square, it will mean that this will just be y prime squared. So that's what you will actually see on this equation. So that's why you end up with this. But the velocity there, you just plug the velocity and you will finally get this equation. All right. Now we are identifying the function f to be this term here, Now if you consider the Euler's equation, you can just see that this function, this df, the differentiation of y with respect to f is just going to be 0, because f doesn't depend on y, but it depends on y prime. So as a result, this is just going to be 0, and then the Euler equation is just going to be, we are only going to consider this term here, and if this term is equals to 0, that will mean this guy inside here, inside the brackets, must just be equals to a constant, because when you differentiate a constant, you are just going to get what you call 0. Now that constant is defined to be 1 over the square root of 2a, right? Now this is where you are. Now if you differentiate this with respect to y, if you differentiate that with respect to y, this is what you are going to have. If you differentiate that with respect to y and you take the square and you square the function, this is what you are going to have. Because now if you differentiate this, if you differentiate this f with respect to y prime, what are you going to have? If you differentiate, if you differentiate f, if you differentiate f with respect to dy prime, this is what you are going to have. You are just going to have 1 over 2 1 plus y prime squared divided by x, but minus 1 over 2 here, and that must be multiplied by 2y prime, and the 2 will just cancel each other. Now if you square this, if you square that, this is what you are going to have if you square that. And also you must square the right hand side too. So that is what you are going to have. And now if you rearrange the equation so that you can have y is just going to be given as the integral of this function, because you are just separating the variables to this. If you separate variables there, this is what you are going to have as your y. Now, by making the following changes of variables or substitution, when you have this x to be defined to be equal to this, and dx must just be equal to this now, and you do the integration, this is what you are going to have for your answer. Therefore y will just be given by this plus constant, and this constant can be we can get this constant by using the initial conditions. Now from this, the parametric equation of a cycloid passing through the origin. So this is just the equation of the cycloid, the equation of a cycloid. And a cycloid can actually be pictured by considering the disc which is actually rolling on the ceiling. Say you have a ceiling here, and you have a disc. Now if this disc is going in this way, so what is going to happen? What is going to happen to this point here? This point here, this point will just be there. But what will happen to a point somewhere here? That point will just be making this a cycloid, it will just be making this a cycloid graph. And I encourage you to actually watch this YouTube video in order for you to be able to understand what is the brachystone problem and how this will behave when you focus at one point on the disc, on the surface of the disc. And of course the center of the disc will just be parallel to the y-axis. All right, now it is also very interesting to see that the cycloid or this brachystone problem, after watching this video, then you can be able to tell me when you want to design the ramp that will actually make this particle to move from point A to point B as quick as possible. Which one are you going to choose? Can you choose this path, or will you choose this path, or will you choose this path, or which one will you choose to make sure that this particle or this ball, remember I told you that this is actually a ball placed at point A. Which ramp will make this ball to reach B at the soonest possible time? Is path 1 or 2 or 3? So just watch that video in order for you to be able to get the clear answer of this, because that will just show you the practical part of this brachystone problem. Right, let us also do the following example 6.3. Consider the surface generated by the revolution of a line concerning 2 point from point 1 to point 2 about an axis coplanar with the 2 point. Find the equation of a line connecting the 2 points such that the surface area generated by the revolution, the area of the surface of revolution is minimum. Now, in this case, we assume that the curve passing through point 1 and point 2 is resolved about the y-axis, is actually revolving around the y-axis. Now, in that case, you can see what is your ds. Your ds is just given by this, and this is, you apply the same thing, and I'm sure I've just shown you in the previous slide how to get that. But now, what is dA? The dA is actually given by 2 pi x dx, but now we know what is dx. Dx is just given by this, which can also be simplified to this, and the 2 pi can be taken outside the integral. Now, in order for you to get the area, then you have to do this, the total area. Therefore, if you integrate this, the total area will, therefore 2 pi will just be given by this equation. Now, if you consider the fact that the Euler equation, we identify f in this equation to be this. That is our f. Now, from there, the differentiation of f with respect to y is equal to 0, because this function doesn't depend on y, but it depends on y prime. So this is what you are going to have. And then when you differentiate f with respect to y prime, this is what you are going to have. This x is actually coming from here. That is this x. All right. Now, if this needs to be 0, if this needs to be 0, it will mean that if this needs to be 0 from the Euler's equation, it will mean that this term here, it must just be equal to constant, and I define that constant to be equal to a. That constant to be equal to a. Now, if you square both sides of the equation and you rearrange and you solve for y prime, this is what you are going to have. Now, that will mean that, remember, dy over the y prime, the y prime is actually defined, or is equal to the dy over dx. So now, if you plug that and then you do the integration, which is nothing else but this is just going to be equals to a divided by x squared minus a squared, and then square root. Now, this is what you are going to have. Now, if you want dy, you are going to have a dx, and then here you have x squared minus a squared and 1 over 2. Now you have to integrate, to do the integral in order for you to find y, this side. So this is nothing else but that is that equation that you are seeing there. Right. Now, if you go and do that integration, of course, from the table of integration, you can also see that this is just going to be given by the hyperbolic function, which is just going to be the cosh. Now the y is just going to be given by this, and then the x will just be given by this. And this is nothing else but this is just the equation of the catenary. Now, what is a catenary? The good example of a catenary is the rope hanging on the poles. For an example, suppose this black are poles, and then you have a chain hanging on these poles. You know the shape of the rope hanging on the poles. So that shape is actually not a parabola, but is what you call the catenary. So it will just hang like this from one rope to the other. So suppose this is your chain, say, hanging on the rope. So the equation for that is what we term the catenary. So it's not the parabola, but it's the catenary, because the parabola will just be a little bit steep. I think you know that. Good. So that is what is a catenary is. All right. Good. Now let us just dive into the second form of the Euler's equation. Now, a second equation may be derived from the Euler's equation that is convenient for a function that do not explicitly depend on x. For an example, if this is 0, what are we going to have? Now, first of all, note that for any function f, the derivative is the sum of the terms. The derivative is the sum of the terms. So this is what you are going to have. Don't ask me where is the dx or d over dx. It's just 1. So this is what you are going to have. Now I want to write this dy over dx as y prime, and then this, therefore this will just be y double prime. As a result, this is what you are going to have. Right? This is what you are going to have. And I also want you to remember that if I have something like this, I want to differentiate that, I need to take into account, if I have two functions called f and g, how do I have the y prime? If I have to differentiate this, I will just have f prime, I apply the product rule, I also differentiate g, and then I leave f. So this is what you are going to do with that equation here. Now, if you do that to this is what you are going to have. This is what you are going to have. And now from there, you substitute, and this, you make this a subject of the formula. If you make this a subject of the formula, all these other terms goes to the other side. So now when you do that, you are just going to have this. This is what you are going to have. Right. Now from there, we can also see that this, the derivative of this can also be written in terms of this. And then here you just factor the y prime. Here you just factor the y prime. So that is what you are going to have. Now, but the last term vanishes in the view of the Euler's equations, because this is the Euler equation, and that must just be give us 0 from what we have done previously. Now, as a result, this final equation will therefore be given by this guy minus this other terms, because this one will just be 0. Therefore, you can just factor the d over the x. So this is what we call, or this is what is termed the second form of the Euler equation, and we only use that when the derivative of f with respect to x is just equal to 0. Therefore, the term that is just going to be left is just this term here inside here, and that term here must also be equals to a constant. It must just be equals to a constant in order for us to get 0 here. All right, good. Now let us also do the following example 6.4 in order to make sense of what we are doing. A geodesic is a line that represents a short path between any 2 points when the path is restricted to a particular surface. Find the geodesic on a sphere. Now in that case, I also want you to watch this YouTube video before you can even attempt this example, so that you can have a clear understanding of what is a geodesic. Now in that case, in a spherical coordinates from the appendix of your books, this is what we have. ds squared is just given by this for the sphere of radius r. But now with dr is equal to 0, therefore this term will just go, and then this r will just tend to be a path, because in the sphere, the shortest distance from one point to the other, the distance from a sphere to one other on the surface, I mean, if this is your sphere, and then you have point A, and then you have also point B, the shortest distance from point A to point B. Yes, that's what it says. So I want you to watch that. Now, if that is the case, now the ds is just going to be given by this equation here. It's just going to be given by this equation here. Right. Now, in this case, the ds, we have to take the integral. If we take the integral, we can take the rho outside the integral, and this is what you are going to have. This is what you are going to have. d phi here. You just apply the same principle that we have done with ds, for dx squared and then dy squared. So this is what you are going to have. And then from there, we identify f to be this function here. Now, if this is a function f, now we have to use the Euler equation. Now, this the differentiation of f with respect to phi is equal to 0, because this function f doesn't depend on phi, but it depends on the theta. Therefore, the only term that we are going to be used is this these terms, because we want to use the second form of Euler's equation in order. But now, in order for us to get 0, this function, it must just be a constant. It must just be equal to 0. Now, in that case, you have f. This is your f minus, and then the theta prime, and then you have to differentiate with respect to theta, this term. Now, if you differentiate this with respect to theta, this is what you are going to have, and this must just be equal to a constant. Now, if you do that, and then you differentiate and multiply through by f, this will just give you this equation. The sine squared is equal to this term on the left hand side. Now, this may be solved for considering the inverse of theta prime. Now, with the results that the d alpha would just be given by this equation here. Now, from there, you can also be able to solve for phi, because you will just separate the variables there and then you integrate. Now, if you separate the variables there and then you integrate, then you can be able to get that alpha, phi is just given as the sign, is given by this equation you are seeing there. Right, now solving phi, we obtain phi is equal to, given by this equation from the previous equation, where alpha is just a constant of integration and beta is just given by this equation. Therefore, we rewrite the alpha, the equation for phi to produce this equation. Now, in this case, we also want to convert to a rectangular coordinates by multiplying through by rho sine theta to obtain the following equation, and you also expand the sign of phi minus alpha. This is what you are going to have if you do that. This is what you are going to have, after the expansion. Now, from there, because alpha and beta are constant, therefore this can be defined as A, and this can be defined as beta. Now, from there, if you plug this to there, this is the equation that you are going to have. Now, from this equation, we can just see that this expression is nothing else but is for an expression for y, x, and z, respectively in spherical coordinates, and which can be written in terms of this. That can be written in terms of this, and that is, which is nothing else but the equation of a plane passing through the center of a sphere. Now, hence, the geodesic on a sphere is the path the plane forms at the intersection with the surface of the sphere, a great circle. And note that the great circle is the maximum as well as the minimum straight line distance between 2 points on the surface of a sphere. Right. Now, let us also consider the function with several dependent variables. We are just going to apply the same thing. Now, in this case, suppose that the function is the function of y1, y2, and y1 prime and y2 prime. And in this case, or simply, we can just write this function f in terms of this. We can just write y subscript I of x and y subscript I prime of x to be like that. Now, if we apply the same thing, therefore the variation equation in that case will therefore become this. Now, we are just going to have y I and then the variation of the I terms. All right, so that's what you are going to have. Now, if we take the derivative of the functional, the derivative of a function of functions, or the generation of this integration, this is what we are going to have. Now, if this, for the several dependent variables, that is just going to be given as the sum of I terms for that equation. This equation will just become this. Now, in that case, because the individual variation, the ether I are all independent, the vanishing this equation, we evaluate alpha for alpha at alpha is equal to 0. Therefore, this term inside the brackets must therefore be equal to 0 in order for us to get this or desired condition. This must just be equal to 0. This cannot be equal to 0 because this is an arbitrary this is just the arbitrary variation. So this is what you are going to have for the Euler equation for multiple terms. Now, there is a condition that the path must satisfy the equation of the surface. Say G given by this equation here, given by this equation here. Now, in that case, such equations was implicitly used in the solution of example 6.4 for the geodesic on the sphere, where the conditions was G was just given by the sum of the xi squared minus the rho squared. And in that case, remember, R was just equals to P, which was just equals to constant. Now, these equations are also called equations of constraint. These are equations of constraint. Now, consider the case in which this function is the function of many variables. For an example, it depends on f is just y and the y prime and z prime. So in that case, the equation corresponding to this the derivative of j with respect to alpha is just going to be given by this equation here. We just apply what we have done previously, because previously it was only y, but now in this case we also have z. Therefore, it must have the addition of the terms with respect to the z. Right. Now, there also exists an equation of a constraint. Now, the equation of a constraint in this case, this is what you are just going to have for the equation of constraint, because this is g in terms of the many variables, which is nothing else. This is the case. Therefore, this is just going to be equal to 0. Now, the variations of y with respect to alpha and z with respect to alpha are no longer independent. So the expression in the parentheses does not separate or separately vanish at alpha is equal to 0. At alpha is equal to 0. So it's not vanishing. Therefore, when we differentiate the g from the previous slide, you remember the g from the previous slide? When we take the dg from the previous slide, this is what you are going to have as your g with respect to this alpha. So that must be equal to 0. That must be equal to 0. Now, because where no terms in x appears, therefore, when we differentiate with respect to alpha, this is just going to be 0. Now, the y of a function of alpha and x is just given by that, and then the z is just given by this, because ny and the ether 1 and ether 2 is the variations which are depending on the y and z respectively. Now, in that case, now if we want to determine, therefore by determining this variation from this equation, and then we plug that to the dg equation from the previous slide, this is what is going to give us. Now, this is what we are going to have. For an example, if you differentiate the y with respect to alpha, what are you going to have? You are just going to have n1. Not n1, the ether 1 of x. So this is what you are going to have. Now, in this case, you can just do the factoring of n1. If you do the factoring of n1, this is what you are going to have. And now this j differentiation of j with respect to alpha, it can be written in terms of this equation here. Now, we can also want to have the differentiation of j with respect to alpha to be equal to 0, because this is the condition for us to get the extremum, minima, or the maxima. Therefore, that must be equal to 0. Now, in order for this whole integration to be equal to 0, because this cannot be equal to 0, because this is the arbitrary variation. Therefore, this term inside here must just be equals to 0. Now in that case, because y and z are both a function of x, the two sides of the equations may be set equals to a function of x, which we denote by lambda negative lambda x, and that negative lambda x is what we call the Lagrange undetermined multiplier, which is just given by this lambda x. So this is what you are going to have. Now, for the general case of several variables, several auxiliary conditions, we have the following set of equation, which is this equation here, where this is Lagrange undetermined multiplier, and then you also have this condition for the surface. Right, now what does this mean? It only means that there are m plus n equations in m plus n unknowns. That means you have 2 unknowns, you must have 2 equations. 3 unknowns, you must have three equations in order for you to be able to solve the problem. Now, the above constrained equation is equivalent to the set of the n differential equations. Now let us just do the following example 6.5. Consider a disk without slipping on the inclined plane. Determine the equation of the constraint in terms of the coordinate y and y and theta. Now in this case, if this will rolls down a certain distance y, as you can see that the y is nothing else but it's just equals to r theta. Now the relationship between the coordinates, which are not independent, is just given by this equation here. Now where r is the radius of the disk, hence the equation of the constraint is just given by this y minus r theta. It must just be equal to 0. Right, now if you do the differentiation with respect to y, the g, you differentiate g with respect to y, this is what you are going to have. You are just going to have 1. But when you differentiate g with respect to theta, this is what you are going to have, s minus r. And these are the quantities which will be associated with the Lagrange undetermined multiplier, which is lambda, the single undetermined multiplier for this case. Right. Now, the constraint equation can also appear in an integral form. Consider isoperimetric problem that is stated by finding the curve of y, for which this function has an extremum, and the curve satisfies the boundary conditions, which is equals to y at a is equals to a and y at b is equals to b, as well as the second functional, which is equals to which is actually given by this equation. Note that a fixed value for the length of the curve is just given by L. This second functional represents the integral constraint. Now similarly, there will be a constant lambda such that the function y, the y of x is an external solution of the function, and then the integral of f plus dx, and so that the curve will just satisfy this equation, which is just equal to 0, subjected to the constraints of y at a is just given by that, and y at b is just b, and then the k, the functional k is just given by the total length or is just given by the total length or L. Right, now let us just do this classical Dido problem. One version of a Dido problem is to find the curve y of the length L bounded by the x-axis on the bottom that passes through the point minus a, x is minus a to x is a, and includes the largest area. The value of the endpoints a is determined by the problem. What are we really want to do? We want to find the curve y as a function of x that maximizes the area above the y is equal to 0 line, consistent with the fixed parameters length. The curve must go through x is equal to minus a and x is equal to a. The differential area here, if you want to get the area here, you just have to multiply y dx. Y dx would just give you the dA. But what is dl? dl in this case, you are just going to get dl by getting the dx squared and then the dy squared, as we have done previously. In this case, in order for us to get to find the extremum solution, therefore the extremum solution, or the extremum area, therefore we have to take the functional for the area, which is this one. Now for the constraints are just given by y at a is equal to 0 and the y is equal to 0 at a and minus a, and the k is nothing else but it's just the integral of dl, and the integral of dl is just the total length of the wire. But now what is dl? From that equation here, the dl, you remember the dl is just that small chop. That is your dl. But that dl is actually nothing else but it's just the vector for the dx and then dy. Right, now if you use the theorem of Pythagoras, like we did it before, dl squared is just equal to dx squared plus dy squared. Now if you apply the same thing that we have used before, so this is what you are going to find for your dl, which can also be simplified to this equation here. Right, now we are just going to plug that in that equation here. Now if we plug that in that equation, that must just be equal to the total length L. Now remember that dy prime is given by the differentiation of y with respect to x. Now in that case, therefore we have determined g. We determined g, we have also determined the f. Now in that case, and we use the function in the differential equation. Therefore the differential equation, if we differentiate f with respect to y, is just going to give us 1. But if we differentiate f with respect to y prime, there's no y prime there. Therefore that is just going to be 0, because in f is just y, there's no y prime. Now for the g, if you differentiate g with respect to y, is just 0 because there's no y there, but there's y prime. But now if you differentiate g prime with respect to y, this is what you are going to have. Now in that case, if you plug these things back to this equation, this differential equation will therefore become this, will just become this, and that must give us 0. If that is 0, it will mean that the whole term here, yes, this will just be 0. Therefore you can rearrange this equation, which can be written in terms of this equation here. It can be written in terms of this equation here. Now from there you can square this function. If you square this function, or you actually don't square, you rearrange the equation, and then you actually integrate with respect to x. You integrate with respect to x. You just integrate with respect to x. So this is what you are going to have, where c is the integration constant. Now this can be rearranged because we want to find dy. Now we rearrange the equation in order for us to find dy, because y prime is nothing else but the y prime is given by this, so that we can be able to do the integration, with respect to y, and then so that we can find y, and the y will just be given by this equation, where ct is another constant of integration. Therefore the maximum area is a semicircle bounded, because this is the equation of a semicircle, where by y is equal to 0 line, the semicircle must go through this point and that point, and which means the circle must be centered at the origin, so that the c1 is equal to c2, and they must all be equal to 0, and the radius of the semicircle is nothing else but is just lambda. Right, now let us also deal with the last part of this chapter, which is the del notation. Now in the analysis that uses the calculus of variation, we customarily use the shorthand notation to represent the variation, and that variation was just given by this, and that can be expressed as short notation. We want to express, which means this, if we want to write this in terms of that, it will mean that the whole thing in there is just going to be given by that. It can be defined by this. If we want to write this equation in terms of this delta notation, which is just a shorthand, therefore it will mean that this is just that and this is just that. So that's why you see this equation over here. Now the conjugation for the extremum then becomes, because we want to have 0, we want to have the condition for the extremum will just be given by this equation here. Now taking the variation symbol inside the integral, because by hypothesis the limits of the integration are not affected by the variation, we have this equation here, but we know what is delta y prime is just given by that. Now if you plug these things back there, this is what you are going to have for your delta functional. Yes, now from there you can just see that the integration of the second term needs to be done by the integration by parts, and then if you apply the same thing that we have done previously, you can just find that this is what you are going to have. Now in order for us to consider the delta y as the variation, which is arbitrary, so therefore the Euler equation will just be given by this equation. Therefore delta j is just equal to 0, requires the integrand to vanish. Therefore this is what you are going to have. Although the delta notation is frequently used, it is only shorthand expression of the more precise differential quantities. The varied path represented by the del y can be thought of the physical of as a visual displacement, as I've told you that this del is just the variation of this. Now this variation is distinguished from an actual differential displacement by dy by the condition that the dt is just equal to 0. That is that the time is fixed. Now I would just like to pause here, and I'm very sorry for the maths, and believe it or not, we will need this maths for the coming chapters. Keep well. Bye.